Hello. Thank you all very much for coming. My name is Doug Hawkins. I work on the JIT team at a company called Azul Systems. That is, I work on the just-in-time compiler inside of a Java virtual machine. And our company is sort of aimed at high-performance Java applications. We support 2 terabytes of heap. I work a lot with low-latency messaging applications, people who sometimes measure performance in, believe it or not, microseconds. And this is going to be my attempt to explain to you what I actually do. What does a JIT do? And ultimately, to try to help you understand what you can do to play nice with the JIT, to let it do work for you so you don't have to do it yourself. And more specifically, our goal for today is to understand this. Yes, array list for each, added in Java 8. This is sort of a simplified view of what it might look like. It takes in a consumer, it's an action, it's just a functional interface, and we call that functional interface for every element in the array list. That's it. This is what we're going to be talking about. And I know you're going, really? We're going to spend 50 minutes talking about 5 lines of code. Well, really more like 3 lines of code. Are you kidding me? But there is actually a lot hidden in that 5 lines. And there's a lot more work that has to be done by the compiler to optimize that than you might expect. Now, the actual implementation of that method is a touch more complicated. It involves a non-null check at the very beginning. They pulled some stuff out into local variables. We'll get to why the author of this JDK function may have done that. And there are these mod count checks for checking if you've modified the collection in the midst of iteration. But it's not that much more complicated than the 5 lines I showed you in the beginning. The first thing you have to understand about the just-in-time compiler is its compiler. Believe it or not, compilers have a lot of universal similarities. At this point, almost everything you can think of is going towards LLVM. LLVM is now actually the default compiler for Clang. It's the default compiler for Objective-C and Swift. Okay, those are all Apple projects. But it's also used by your graphics cards, your PlayStation 4. Microsoft is using it for C#. And the list goes on and on and on. Because most languages, no matter how different you think they are, I think they're the same. But a JIT is a bit special, particularly the one in Hotspot. It's what's called profile guided, which means it wants to have information about what your program is going to do to perform optimizations. The JIT in Hotspot isn't necessarily a great static compiler, but it is a good profile-guided compiler. And that's rather different from a traditional C compiler like Clang or GCC. But more than that, it's also speculative. By virtue of being inside of a VM, this little closed world, we can say, I'm hoping the profile is perfect, knowing that it probably isn't, as long as we have some other backup strategies. The compiled code doesn't have to handle every single case, which also separates a JIT from a traditional C compiler. So to actually understand the example, the 5 lines of code I showed you, we're going to have to understand a whole bunch of things. We're going to have to look at some static optimizations. This is what C, C++ compilers would do. We're going to look at some of those speculative optimizations that Hotspot does. We're going to look a little bit at interprocedural analysis, multiple methods being analyzed together by the compiler, and something that's very specific to the JIT, de-optimization. To get away with speculating, we have to have a way to deal with speculations that fail, and that is de-optimization. And we're going to look at 2 different scenarios for that. And more importantly, we're going to see that all of these things fit together. I have a basic view that all compiler optimizations don't matter, except when they do, and they matter in aggregate. No one compiler optimization is necessarily a huge win. It's how they all fit together that gets the payoff. So the real goal in all of this is I want you to understand what you can rely on the JIT to do for you. There are a lot of things it can do for you. There are ways you can write your code that are amenable to the JIT. Fighting it, I promise you, is a lost cause. You do not have control. You should accept that. You can only go with the flow. Fighting it will hurt. But before we get to that, I wanted to have at least one slide on how does the JIT even get triggered? What does the workflow look like? Well, in Hotspot, or OpenJDK, you start off running in the interpreter. Not every VM actually has an interpreter, but Hotspot does. The interpreter is not very fast. But what the interpreter is doing is tracking how many times each method in your system has been called. And once your method has been called enough times, it will get compiled by the first tier JIT in Java 8, C1. C1 is a very fast compiler. It's not a very smart compiler, it's very fast. But on some level, its more important role in Hotspot today is it does the profiling. We have to actually do some profiling, following your application around, figuring out what it's going to do to decide how are we going to do these speculative optimizations in the next compiler, C2. And that's the final optimized tier. The actual tier workflow is a little more complicated than this. There's some interesting edge cases, but this is how the average method flows. Now C2 takes that profile and does some optimizations, assuming that that profile was perfect, and if it's wrong, then we'll have to do some sort of de-optimization and bail to the interpreter, which will be slow again, and then we'll repeat the process having learned from the mistake. You see at the bottom here, I've labeled what's going on in terms of profiling. There's actually a short period at the very beginning where it's not profiling. That's because our applications do all sorts of weird one-time setup things that just aren't normal. They're done once at the beginning and that's it. There's no need to include them in the profile. Whether it's dependency injection, filling a cache, what have you, there are these sorts of things. Class loading, all sorts of things happen once at the beginning. So we don't include those in the profile. Then we have an actual sampling period where we're building the profile. Then we get to full speed, hopefully, unless we were wrong. And then we drop down. And then for most of the common types of de-optimization, you're going to end up doing a resampling. Not always, but most of the time. And then after you've done this a few times, you'll reach a stable period of performance. But it does take a while. Okay, back to for each. Where should we start? Well, one of the things that makes Java complicated is there's actually a lot of code here that you didn't write, but it's implied by the safety of the VM. There are null checks everywhere. There are bounds checks everywhere. And you might actually think that like caching a bound would be good, but it's actually not. So rather than using this.size, I'm going to make this simpler for the JIT as our starting point by switching from ArrayList to a theoretical ArrayStream class. And the only difference is the size of the ArrayStream is the size of the array. So I don't have this.size, I have this element data.length. And this is actually simpler, believe it or not. And now we add in all the other stuff I just mentioned. Before I can access this element data at the top of the for loop, I have to first access this. Can this be null? Well, if it could, we have to throw a null pointer exception. Could this element data be null? Well, if it could, we have to throw a null pointer exception. All right, then we have to do this again inside of the loop before we access the element of element data. And then we also have to check the bounds. This is where we get the safety guarantees. So we have to check if I is less than 0, we throw an array index out of bounds exception. If I is greater than or equal to the element data length, we do the same. And we also have to check that our functional interface object action isn't null either. We got to do all of these things. They're all hidden from you, but optimizing them is actually important to the performance. Fortunately, we can throw out one right away. As implemented in the VM, the null check happens before the call. So if we're in a method, this isn't null. Before the call, we have to check that it's not null. After the call, we don't. So the two null checks against this, we don't need them. Any other variable, we need them. But this is OK. OK, let's move on to a different bounds check. Let's look at I less than 0. This one's a little bit interesting. I starts at 0, and it's incremented by 1, and that's it. Does that guarantee that I is between a positive integer or 0? No, no. We wrap arithmetic in Java, so it could still be a negative number. But we can say I is less than this element data.length. And the length of an array has to be a positive integer or 0. I.e., it has to be 0 or int max. So in the low side, we can say I started at 0, and it has to be less than int max. And we can constrain its range that way. This is actually a type in a mathematical sense. And now we can say I is definitely not less than 0, and that's dead code, and it goes away. Compiler does this sort of reasoning for all the time, not just for arithmetic types. We'll see an example of that towards the end. Now the upper bound. I greater than or equal to the element data.length. The way we handle this is a little screwy when you first look at it. The way what we do is we actually turn greater than or equal to the element.data.length into I not less than the element.data.length. Like, why? Why would you do that? How is this making it simpler? This is a process called canonicalization. What we're trying to do is remove the number of different patterns we have to deal with in the code. If you were doing this for a file you were parsing, you'd call it data normalization. That's all it is. We're reducing the number of patterns in the code. So now we only have to worry about less thans. We don't have to worry about greater than or equal. That's one less thing to worry about, and that makes things a bit easier. We can now actually see that the test at the top of the for loop is also I less than element data.length. And we've already computed that once. And so we actually already know the answer. If we're inside the loop, it's true. If we're outside the loop, it's false. But inside the loop, it's true, and we don't need that check. Not true is false. This is how it works. Now, I've labeled this as common subexpression elimination. It's actually really an optimization called global value numbering, but nobody other than a compiler nerd knows what that means. So I'm just going to call it common subexpression elimination. And this starts to get at why this dot size is harder. This dot size to the compiler has no relationship to the element data.length. It has to do the other check. It has to do the element data.length check, but it was invisible to you. And when it's checked against the length of the array in the for loop, we're checking the same thing twice, and we can make them into one check. Otherwise, you have this hidden check that you have to keep, and you didn't know it was there. So storing it into a variable actually isn't better. We have a way to deal with this problem, but it's still not as good as just using the array length. Okay, we've gotten rid of a lot of checks. That's good. What's left? Well, we have null checks for the element data, and we have a null check for the action. What can be done about those? Is there a way we can prove that element data isn't null at the beginning? That's hard. What about inside the loop? Well, that's the same. And the action, maybe. So we have a strategy for this. We're not always able to get rid of all the null checks. So we try to make them as cheap as we possibly can. And the way we do this is fascinating. You would think that the code that's generated when the JIT gets a hold of it is something like what I've shown here. It says, if this element's data equals null, throw a null pointer exception. Then access this element's.length. No, that's not what we do. We actually just run this element's.length. This is actually the machine code here for what's produced. RSI is elements, and 8 is the offset of the length. Now, imagine RSI is null. In machine code, what happens if you dereference a null? Or if you prefer, in C, what happens if you dereference a null? You get a segmentation fault. Right. And that's exactly what happens. Your VM crashes. Okay, not exactly. It's a contained environment. The way we deal with this is we've said, oh, we know we might crash because of this, and we install a segmentation fault handler. And so the VM does actually segfault. We trap through the hardware, through the OS, and then back to our segfault handler, and we say, oops, I meant throw a null pointer exception. How is that better? Well, branches in hardware are actually pretty expensive. We'd like to avoid them at all possible. Even though this one can be perfectly predicted, it's putting pressure on a scarce resource, the branch predictor table of the hardware, and we prefer not to do that. So instead, there's already conditional logic in the memory subsystem of an Intel chip. We just use that. And this works as long as nulls are rare. We have profiled all of you, and we have made the bold conclusion that you are all semi-competent and do not raise null pointer exceptions all the time. For those of you for whom that's not true, we do have an optimization for that as well, but I'm not going to show it to you. If you produce null pointers exceptions all the time, we have a handling for that too. But this is for the common case where we don't get a null pointer exception. And having a single instruction with no branch is actually faster. Until you hit the null. When you hit the null, this is way slower. Trapping through hardware and the OS is painful as compared to a branch operation. But if that almost never happens, this works out just fine. So what happens if it happens a little bit? Well, let me show you. Here's an example of null checks. And what I am doing is I have a for loop, and I am calling a method, hot method, 20,000 times with the string hello. I happen to know that 20,000 times is enough to get hot method just-in-time compiled. But to prove that it's being just-in-time compiled, I'm going to run this example with a flag called print compilation so that you can see that that does indeed happen. Now, the just-in-time compilation happens by in-queuing the method for some other thread to get to and be compiled at a later point in time. I want to make sure that's done, so I just sleep for 5 seconds. And then we start pushing our luck. We start actually showing this hot method nulls, which it is not ready for, because nulls have never happened before, and so the VM assumes that they won't happen, because that's usually true. And here's the implementation of hot method if you were curious. That's it. Now we'll run it. Here you see the output of the VM when you're using print compilation. It's showing me the methods that were compiled. The second one that got compiled is my hot method. And then I start showing it nulls. That's the printing out of the tempting fate line. One null is okay. Maybe that was just an aberration. We'll let that slide. 2 nulls. Now you're pushing it, but we'll let that slide too. 3 nulls. No. Apparently nulls are a thing we have to deal with, and we go, they're happening often enough, we'll switch to using a branch. You apparently are only semi-competent. And that's what you're seeing there. The line with made not entrant out to the side is actually saying, that compilation we made before, optimistically assuming that nulls weren't a problem, we were wrong. Let's throw it away. Given enough time, it will compile again, not making that assumption anymore. And that's one of the ways we deal with null checks. But we'd really just like to get rid of it altogether. And it turns out we actually can do that in many situations. Now, you would think that this element data would be a good candidate. We already had to check it once outside the loop. Can't we do that common sub-expression thingy and say that it didn't change inside the loop? That turns out to be a bit hard. We will get there, but it's harder than you would expect. To do that, we'd actually have to require that we know a whole bunch of things don't change every time we evaluate the expression. We'd have to know that null doesn't change. Well, that's fine. It's a constant. We'd have to know that this doesn't change. That's fine. It's a constant within the method. But knowing that this element data doesn't change, that's harder. The easy one, believe it or not, is actually the local variable action. It's like, but that's inside the loop body. How are you going to check it before you run the loop? That's not legal. I didn't say I had to run the whole loop. And this is where we get to a rather interesting optimization. But the reason we can't do it for element data is because it's not because it can't be changed by this thread, the other thread. The compiler actually doesn't care about that. If you don't tell me that this variable is volatile, the compiler has no requirement to care that some other thread changed the variable. But we do have to respect single-threaded semantics. If this thread changes it, we will have to actually check. But action is easier. It's a local variable, not a heap variable, so we don't have to do that. But we do have to find a way to check it before we start running most of the loop. And to do that, we perform an optimization called loop peeling, where we take the first iteration of the loop and we break it off into its own piece of code. And then we actually only do a loop for the remaining n-1 iterations. And by doing that, when we do the first iteration of the loop, we prove that action isn't null, and we don't have to do that again. So in the rest of the iterations, the action check simply disappears. That is nice. It's also a little terrifying that we play these games because of the multi-threaded aspects. You'd like us to do this optimization for element data, and as I said, we can, but it also means writing multi-threaded code is hard. The same optimization that lets us do it for element data or for action causes you problems when you're writing multi-threaded code. It's actually legal in the consumer thread example on the right to say, rather than reloading shared done over and over again, you didn't tell me another thread can change it, so I guess it can't change. So I'll just store it in a local variable, and if it was false, you'll just spin forever. That is perfectly okay, according to the language specification. In C, this is actually undefined behavior, and the compiler is free to burn down your house. That's an acceptable implementation. In Java, you just spin indefinitely. That's an acceptable implementation. So why was this hard for element data? It doesn't seem like it should be, but it's the single-threaded semantics. We have to oblige changes in this thread, and we have this function call sitting there. The function could be anything whatsoever, including changing element data. And so we can't make a lot of assumptions. Like, but you're like, hold on, this is array stream. And I saw your slide earlier, and element data was final. Does that mean it can't change? Sadly, the answer is no. Reflection is allowed to change final variables. So any function call, we have to assume that you do every evil thing possible and throw away optimizations when there's a function call. Until recently, that actually meant we could not conclude that the characters inside of a string were unchanged. I said until recently because we said, we make the rules, we'll let that one slide. And we did that in the new VM. But final variables, we have to assume that they actually can change when they are instance variables of an object. That's not true for static variables of a class, but it is true for instance variables of an object. There is actually work going on in the OpenJDK right now to track whether or not you are evil. That is, did you use reflection to change that final variable? We assume, like with the null pointer exception, that you are not an evil person, but we are not entirely confident of that, so we follow you around, and if you turn out to be evil, we have to de-optimize. This is how we deal with the API we've created. The other way we can deal with it is we can look inside the function call and see what's there. And if we can prove that you don't use the evil things, then we can still do all the cool optimizations. And in Hotspot, the only form of such interprocedural optimization is inlining. And inlining is a very simple concept. You just copy the code of the callee, the method you're calling, into the caller, and you do any substitution. So for instance, I have this square method here, which I'm passing a value of 9. You can probably imagine what the implementation of square looks like. It's, return x times x. And we can inline that and say, well, that's really 9 times 9. And then we can perform the world's most boring optimization called constant folding, and you say, you know what? 9 times 9 is 81. Yes. Brilliant. But it does get rid of a call. And it does let us prove that no evil things were used. And eliminating the call is big. It is 10x performance. It's hard to say getting rid of the call opens up new optimizations, so you can't quite cut it that cleanly, but it's big. And to get that to happen, you need to write small methods. Inlining in Hotspot is restricted mostly by bytecode size. There are other factors, but this is the one you actually have some control over. And the cutoff number you really need to know is one called the max inline size, which is 35 bytes. It's not a lot of bytecode, to be honest. Hotspot really likes lots of little methods, and that's what you should write. It will glue them together like mad and make it perform well. I have actually seen it glue together 150 methods into a single compilation. You do not want to write 150 methods all as one free-form piece of code. I mean, it might run well, although at that size, we also have a limit called the huge method limit where we just refuse to JIT your code. So you really actually are forced to write small methods. You have no other choice. We will put them together for you. You just need to trust us on that. But let's say we can't get rid of this inlining and get rid of the call. Looped optimizations are also still big. If I pull this element data out into a local variable, kind of like we did with action, then that is actually still a 25% win in throughput. You might think less code is better. You might think less local variables is better. You're probably actually wrong. More local variables is better because they're easier for the compiler to reason about. Stuff on the heap we have to assume is mutable. Stuff that is local we can actually look at and say, okay, you don't change it, that's easy, even when there's still a call. But there is one big stumbling block left for Java. Everything is dynamic. Everything. How do we optimize this? It's dynamically loaded, it's dynamically linked, it's lazy initialized, every call is dynamic by default. How do you make this work? The method we're talking about is an arbitrary function object. The whole point for it to exist is that there could be hundreds or thousands of them in your program. How do we know which one you're using? Well, we have all sorts of games. We actually have 4 different strategies for this. Yes, we have a backup for our backup for our backup. That's how important it is to get rid of calls. We're going to look at 2 of them, plus a little bit of one more. There are 4 different ways. Static analysis, which is what a C or C++ compiler could do. There's something called class hierarchy analysis, which a statically linked C or C++ compiler could do. Or this thing called type profiling. We won't talk about the last one. Let's take an example. Here I have the use of a function object called func, and I set it to square, which is just a function object that squares numbers. Surprise, surprise. And I'm going to compile it by calling this 20,000 times inside of a loop, but I have this little helper method because I want to see what happens when that helper method gets compiled in isolation. Because inside of main, we actually statically know that function is a square, right? We can do this type deduction. We can say, it was a square, so that means function is really a square, which means the thing that we passed to apply was really a square, which means we actually know the type we're using. A C++ compiler could do that. But when we're only talking about apply itself, the helper, in isolation, that doesn't work. But let's see what the VM does anyway. If I were to run this, and I ran it with print compilation, and I get it to show me the inlining decisions, which I'm doing by turning off background compilation so I don't get interleaved output, and using unlock diagnostic VM options so I can do print inlining. I would get this output. At the bottom, there's a compilation of main, and there it did actually inline monomorphic apply, which is apparently at bytecode 15, and square apply. And it did this through static reasoning. But if you look above that, there's monomorphic apply, and it also inlines square apply. How does it know that the value coming in to apply is always a square? How does it know? The static reasoning doesn't work. This is what works for main. You can follow the line, but there is no line. You're just starting from func. How does it know? It uses what's called a closed world assumption. It takes advantage of the fact that classes in Java, at least in Hotspot, are lazy loaded. That's actually not required by the spec. And says, right now, the only function your program has ever used is a square. Maybe there are other functions, but I don't know about them. So the only possibility is that the function variable is null or it's a square. So we're either going to raise a null pointer exception or we're going to call square apply. That's the reasoning. And this works. But what happens if you load another class? What happens if the world isn't closed? So a C or C++ compiler can do this because, if it's statically linked, because they know the world is closed. But in Java, the world is always open. You can always load one more class. Heck, you can just make a class up out of thin air and load it. What would you do? Well, this is where things get interesting. I have more or less the same example. But I have 8 apply methods. They're all going to make the same assumption. I'm going to wait for them all to compile. And then I merely suggest that, there might be another class. There might be, I don't know, a square root. Note, I don't actually use the class. I just load it. I don't even instantiate it. No, I didn't even create a square root object. I merely loaded it. That's it. Let's see what happens. Okay, all 8 methods are compiled. Excellent. What is that? That is all 8 compilations saying, oh, apparently there's something else than square to worry about. I'm going to give up on my strategy and try again. And they all have to be de-optimized immediately because there's actually no type check before the call, or the logical call. And to do that, the VM actually has to stop the world. This is another type of stop the world pause in the VM that you probably didn't know about. And to show you that, I actually ran with the flag print safe point statistics, which will show other point types of stop the world pauses. So we're seeing the enabling of bias locking. We're seeing a de-optimization. There are other things than just GC. But this is how we deal with the fact that our profiling, our closed world assumptions, might not be the full story. That only works on a global level for the entire program. It has to be true everywhere. You can never load a second type. That works nicely some of the time, but fails miserably other times. To deal with that, C1, or the interpreter, gathers a profile as well. And we track the types used at every call site. So, for instance, there's actually an XML file you can look at if you use log compilation to see this. And inside of it, we'll see, hey, I'm using a class square, and I'm using a class square root, and 19,900 times I've used, in this case, square, and this was a slightly different example, but 3,000 times I had used square root. You can go and find this information. It's actually there if you really wanted to see it. And we can then use that to try to inline again. And this is actually call site specific. So if you have a call site that uses one or two types, we'll do it with extra guards. So we'll say, if the function is a square, inline that piece of code. And then we might say else deoptimize. It's called an uncommon trap. We'll do the same thing when you add a second type. And then after that, we just give up and we do a virtual call. This works much better than you might think. It works for 90 to 95% of your call sites. You're not really writing very dynamic code, truth be told. 90 to 95% of call sites use one or two types, and we still get to inline. This is something you only get from profile-guided optimization, so it's not something your average C or C++ compiler does out of the box. They can do it, but it takes some extra work. You're getting it just for free. This has slightly more overhead than the strategy from before. It's like 3 to 5 nanoseconds on this laptop, but it's still really fast. And getting rid of the call is a 10x win. But there's still something really odd about the example I just showed you. Why don't I just put a call down the else path? Why isn't that just a virtual call? Why do you trap and go back to the interpreter? It's because it's a call. Behind calls lie all evils. All the things that hurt loop optimizations could be hidden behind that call. By leaving that case out, we get to do all sorts of cool things. You get to do them anyway if you pull the variable from the heap into a local variable, but if you don't, this is a good. So did we solve the problem with this piece of code? Well, no. The trouble with the action accept call is its whole point is to be what we would call megamorphic, to use more than two types. That's the whole point of taking in a function object. If you're lucky, we inline for each into its caller, and we have the information, and this all just sort of goes away. But if you're unlucky, and that doesn't happen, we're stuck with a call. And then we have to assume that this size could change because it's on the heap. And we have to assume that this element data could change because it's on the heap. And that's not great. Unless you're the author of this JDK method and you said, I'll pull them out into local variables myself. This makes it easy for the compiler. Most of the time you don't need to do it, but this does work. There's another assumption actually built into this. The author of this method is assuming that the function doesn't change the array list itself. Is that a valid assumption to make? Well, if you're the author of the API, it is. It actually says on array list for each, or for each in general, the function is not allowed to mutate the collection. The compiler doesn't get to assume that. If you want to write really convoluted code, that's your choice. and it has to oblige you. But the author of the class itself can make a stronger line. And that's what they've done. So did we accomplish the goal? Sadly, no. No. 50 minutes is not enough to explain 5 lines of code. I'm sorry, it's just not. There's a lot that goes into a compiler. The hoisting I showed you is really just the first step to a whole host of other loop optimizations. We could do loop unrolling, we could do loop unswitching, we could do vectorization. All of these things will make things go much faster. I didn't even explain to you how it interacts with the garbage collector. That's interesting in and of itself. And I didn't even explain to you how we handle this.size. The answer is we do a check and we put an uncommon trap before the loop. But we do have to do one more check. Comparing against the array length is still better than that. But we can put all these strategies together and make your code that's very dense and expressive quite performant on average. What I'd really like you to take away from this is that a JIT and all compilers are really just complicated pattern matchers. To be honest, we write glorified regexes. That's all we do. We're looking for patterns in your code that we can optimize. And I'm sure all of you have written a regex. And you probably had to do it to process some log file. And in doing so, I'm sure you handled every single case the first time perfectly. No, you handled the common cases that you were actually in the example files you had. That's what we do too. If 9 out of 10 of you do one particular pattern, we're like, hey, if we can recognize that pattern, we can make it better for 9 out of 10 of you. What about that weird guy? Too bad. We're going to try to make as many people happy as we can. So what we actually like is normal code. And normal is defined by you. Whatever most of you are doing, that's normal. We don't like weird code. If you think you're a special snowflake, prepare to be treated as such. We like small methods. We don't like big methods. We like immutability. We don't like mutability. We like local variables. And strangely enough, we don't like native methods. They're black boxes we can't analyze. We don't like them. In essence, what I'm telling you is what is good for you as a programmer reading your code is good for the compiler reading your code. Write nice, clear, concise code and trust that we'll do a pretty good job. That will be true most of the time. Now, this sort of information is sadly rather hard to come by. Most compiler writers like to go sit in the corner and talk to other compiler writers, if I was being honest. And we forget that we actually have you, users, that maybe we should explain to you what we're doing and why. And so that's why I kind of like doing this. And there are at least a few other people who do as well. My colleague, Neet Sanwakart, who spoke at Devoxx UK recently, has a blog where he talks about a lot of these interesting issues. And there's a guy at Oracle named Alexei Shupalov, who is their performance tuning czar. He actually wrote a much more extensive explanation of our vcall, virtual call elimination techniques, if you have an hour or two to read it. But there is some stuff out there, but you have to go and work to find it. If you want to start poking around yourself, I'd recommend you try a tool called JIT by Chris Newland. It's a GUI for letting you see what's going on inside. As you can see, there are all these interesting flags, but if you don't want to have to memorize those flags, JIT is pretty cool. It'll show you what got compiled. It'll show you what got inlined. It can actually even show you a triple view of Java code versus bytecode versus machine code if you're so inclined. And it will tell you, I think you would have liked that to be inlined, but it didn't get inlined. It'll highlight that for you. And it has a companion tool called jar scanner, which will actually yell at you if you have methods over that 35-byte magic limit. So it's pretty cool. And if you found this interesting, and you can tolerate listening to me for a few more hours, I do have a set of videos that go into far more detail on these sorts of things that you can find on O'Reilly's website. So, I hope you learned something about what a compiler does. It's not actually black magic. It's actually pretty simple. But there are some surprising corners where things that you would think we'd be good at, we're actually not terribly good at, and we can't be, like calls. We have to get rid of them. And we can do that often, but not always. So now you have some idea of what we do, and please feel free to ask any questions. All right? Well, thank you all very much for coming.